We're going to prove that this R, where we take ordered pairs x, y, and a cross a, such that x squared is y squared, that this is an equivalence relation, 1, and then we will compute the distinct equivalence classes, and my set A is all integers between -3 and 3. So to prove that R is an equivalence relation, we must show R is reflexive, symmetric, and transitive. Okay, reflexive says that for every single element in A, we need A comma A to be in R. Why is this the case? Well, if we let A in A, then as A squared equals A squared, we see A comma A is in R. Okay, so thus R is reflexive. Very nice. Symmetric. So we suppose you have something in R. So we let A comma B in R. We need to show B comma A is in R. Well, AB in R, it means A squared equals B squared, okay? Equivalently, we can say B squared equals A squared. It's the exact same thing. I'm just writing it on the other side, meaning B comma A is in R, okay? So thus, R is symmetric. Okay, so we have reflexive, we have symmetric. Now we will prove transitive. Transitive, we need to begin with A, B, and also B, C in R. We need to show, maybe I'll write this here, that A comma C is in R. Okay, very nice. AB, we need to unravel what this means. AB in R means that A squared equals B squared. And BC in R means, well, we will have B squared equals C squared. Now what do I need for AC to be in R? I need A squared equals C squared. Do we have it? The answer is yes, because both of them are equal to B squared. So let me just write that. A squared equals B squared, and that equals C squared, comma, showing that AC is in R, because A squared equals C squared. This means R is transitive. Okay, so I have shown R is reflexive, symmetric, transitive. Therefore, R is an equivalence relation. Okay, fabulous. Now, oh goodness, there we go. Part B, compute the distinct equivalence classes. What do we know about equivalence classes? Well, maybe I will remind us about this in red. X in A. The class of X, this is a subset of A, and this consists of all elements, let's say Y in A, such that X relates to Y. And we know, for instance, that two equivalence classes are either equal or they are disjoint. They're equal provided the representatives are related, and they're disjoint if two different representatives are not related. What else do we know about equivalence classes? Well, we discussed that the equivalence classes they form a partition of A, meaning that the union of all of them is capital A, and that they are disjoint, as I mentioned. Okay, well, that's just some background we can use in the calculation. So let's get to calculating. The first thing that you notice in this definition is you start with x in A. So take something in A. Minus 3 is in A. So I'm going to start with the class of minus 3. Well, always you put your representative in the class. This will be the case for any equivalence relation. Then you will add all the other elements in A that are related to minus 3. Well, minus 3 squared is 9. What other things in A square to be 9? Well, it's just this, right? So these satisfy x. 3 satisfies 3 squared is minus 3 squared. Okay, so this is the class of minus 3. Okay, now we need to keep computing because this by itself is not all of A. So you pick something in A, not listed yet. I can do, for instance, minus 2. Then the class here will have minus 2 and also positive 2. Okay? Now I keep computing because these two classes do not union to all of A yet. Pick something else. Well, I could pick minus 1. I'm sort of reading elements left to right in A, which is a fine way to go about it. Minus 1 does not appear yet. Its class consists of minus 1 and 1. Minus 1 always because we have an equivalence relation. But 1 for this particular one because 1 and minus 1 are related. They both have squares equal to 1. Now, you look at all of these. Is this all of A? Not yet because we are missing here. Now, this class will contain 0, but is there anything else? 0 squared is 0. Is one of those other numbers square to be 0? Well, no. This is the only thing in this class. Now, you might think, okay, now I'll do the class of 1 and 2 and 3, but they're already up here. So these are, if you look at this word, distinct. This is what I have listed. You will know you are done when every single element of A is listed in one of the classes. And you will know they're distinct when you don't see the same set written again. Okay? Someone else, so this answer is done, okay? Someone else may have represented it differently. They may have done this. And this is also check, correct, because this is the class of 3, 2, 1, 0. This is just a different choice of representative for the same class. This is okay. It's just a different way of writing the exact same thing. Okay? This problem is a calculation rather than a proof, but it involves relations and the concepts of symmetric and transitive. Now in both of these, we have the same underlying set A, 1, 2, 3, 4. And in this one, which we will do first, you notice you look at R, it is not symmetric. Okay, we want to find the smallest relation on A that, first of all, contains this and is also symmetric. So S equals. If I look at this part first, it will contain 1, 1, 1, 2, and 1, 3. And then, now I need to think about S being symmetric. Symmetric means if x comma y is in the relation, then y comma x is in the relation. Well, I can take, to get the smallest one, the only things I'm going to add are what I need to make, to have y comma x for the elements that are already there. So first of all, 1, 1. Well, when I interchange the first and second coordinates, I get 1, 1. Okay, that's there. This one, 1, 2, interchange, 2, 1. I need to add this. Then 1, 3, interchange, I get 3, 1. And now I stop. You notice that this is symmetric, and if I add anything else, it's not going to be the smallest. And of course, if I take anything away, it either will not be symmetric or it will not have R as a subset of S. For instance, if I remove this one. Okay, so this is our answer. We're given a set relation R, and in fact, this R is symmetric. But that's not what we're interested in. We want to find the smallest relation S on A that contains R and S is transitive. This is not a transitive relation. Maybe before I begin, let me put a line and I will remind you what transitive means. So transitive says if, well, we want S to be transitive, so if AB and BC are both in S, then AC needs to be in S. The way that I would always or typically think about this in class is you have the middle ones matching and then you have AC. It's a way to think about this concept. So let us begin here. The first thing I'm going to do is make sure that R is contained in S by adding the elements of R. And now I need to think about this property. Well, you might look at this and see here we have 1, 4, 4, 1, the middle ones match. Therefore, we must have 1, 1. Okay, but you are not finished. You might think you are for half of a second because it only appears that's the only middle term, but you see, well, if I continue with my little work box underneath, if I write them this way, 4, 1 and 1, 4, these are both in S. And now you see the middle ones match. You must have 4, 4. So this would imply 4, 4 should be in S. So I need to add 4, 4. Now, that's it. You can test every time. For instance, 1, 4 and 4, 4. But that gives you 1, 4 already in the relation. Or 4, 1, 1, 1, 4, 1 already in the relation. This is transitive, and it is the smallest transitive relation on A that contains this one.